Hey, my friends. Today we're going to do some practice with the combined gas law. And instead of taking notes on a Google sheet or whatever, I'm using the Jamboard. You should have these practice problems in your guided notes. And I'll highlight what I want you to have in your guided notes. So let's go through these problems together. I have 4 of them. The first one says hydrogen gas was cooled from 150 degrees Celsius, that's a variable, to 50 degrees Celsius, that's not a variable. It looks weird. Oh, technology. So then I'm telling you that its new volume is 75 milliliters. That's a variable. Oops. And what I want to find out is what was the original volume. So I don't know that one. I always think it's so handy to write down the variables. If you're looking carefully, we have a temperature. It's cooled from, so the initial temperature is 150 and the final temperature, T2, is 50 degrees Celsius. The units are important. Put the units there. It says that its new volume, so its final volume, V2, is 75 milliliters. And it asks for the initial volume. So we do not know V1. It's a question mark. It's unknown. To solve this problem, the only thing that's changing is temperature and volume. So let's get the combined gas law written down. We can cross off any variables that aren't given or don't change. Temperature changes and volume changes, and the other ones aren't given. So I'm going to cross them off. That leaves me with the relationship between volume and temperature, which was one of the simple gas laws we talked about before. So when I cross off the extra stuff that we don't need, we get V1 over T1 equals V2 over T2. Now, as I alluded to in my screencast earlier this week, I think it's much easier to deal with these equations if they are in a linear form. So if you cross multiply. And if you cross multiply this, then you're going to end up with this equation right here. All I did was cross multiply and I got V1 times T2 equals V2 times T1. And then we can solve for the unknown. So if we're looking at the problem right here, the unknown is V1. So I need to mathematically get V1 alone. And the way I can get V1 alone, which is this variable right here, I have to undo that multiplication sign. So I'll divide both sides by T2. When I do that, T2 cancels, and I'm left with the equation V2 times T1 over T2. But before you get ahead of yourself, look at the units of temperature. They're in Celsius. And whenever we do any of these problems, any of our relationships have to deal with the temperature in Kelvin. Do you remember how to get the temperature in Kelvin? You add 273 to it. So I'm actually going to go back and do that right now. And moving forward, if I have a temperature that's not in Kelvin, I'm just going to add 273 to it. The temperature has to be in Kelvin. In order to use our gas laws, we need to have the temperature in Kelvin. Kelvin is the temperature that describes the motion of the particles. So you just add 273 to your Celsius temperature, and it will give you your temperature in Kelvin, which is super handy now because I know V2. V2 was 75 milliliters. I can see it right there in my problem, 75 milliliters, times T1 in Kelvin, which was 423. Oops, okay. Divided by T2, which is 323 Kelvin. Let me do some math. I get as my answer for V1, 75 times 423, quantity divided by 323, I got 98.2. 98.2 what? Well, let's look back at my units right up above. I've got Kelvin in the top and Kelvin in the bottom. Just like dimensional analysis, we want to cancel out identical units on the top and bottom. And so we're left with units of, the only units left over are milliliters, which honestly should make logical sense, right? V1 and T1 are on top of each other, which means they're directly related. They're divided by one another. So what's happening to my temperature? Well, my temperature is cooling off. So my initial temperature is hotter than my final temperature, which means that my initial volume should be bigger than my final volume, which exactly is what it is. So what do you need to have in your guided notes? Let me highlight it in yellow. Always have the variables written down. I think it's so helpful to have the variables written down. And then you don't need to have the combined gas law written on there because we crossed off the variables we didn't need. But the simple gas law, the relationship between V and T, that should be there. Now, I think the way to solve this problem is to do the cross multiplication and then isolate for the variable. So I'd want to have the isolation solved for. And then obviously where you plug in, we want that. And yeah, we want an answer too with units. So it's almost everything, but it's not almost everything. Make sure that what I have highlighted, you have in your guided notes, and we'll do problem 2. Okay, so problem 2 says that we have a gas at 22 degrees Celsius. That's a variable, and we're going to have to put it in Kelvin. Oh, darn. The pressure is 405 millimeters of mercury. That's also a variable. It then says that the temperature changes. The temperature cools down to 0 degrees. That's a variable. And it wants you to solve for the final pressure. What is the resulting pressure? So we're solving for pressure. So yeah, I definitely want you to have the variables written down. So what are the variables? Well, we said that the initial temperature is 22 degrees Celsius. That's T1. And then I'm just going to go ahead and add 273 to it right off the bat, which gives me 295 Kelvin. If you forget, you're not going to remember to go back and add the Kelvin onto it. Okay, the pressure that it's at is at 745 millimeters of mercury. We use atmospheres in this class, so we're going to need to convert it, but no prob. We'll get that done. It says when the temperature is changed. So my final temperature, T2, is 0 degrees Celsius. But again, let's just add 273 to it, so it's in Kelvin. So that's 273 Kelvin. 0 plus 273 is 273. And it says, what is the final pressure? So P2, well, that's unknown. That's what we're solving for. Let's take a look at the combined gas law. I'm going to write it over. Looking at the combined gas law, temperature is given and pressure is given. Volume is not given, so it implies that it's not changing. And number of moles isn't given. So I'm going to cross off V and N on both sides. And that gives me the direct relationship between pressure and temperature, which I'm going to write down again. Since they're divided, it's direct. So if we look at my temperature is cooling down from T1 to T2, which means my pressure also should go down. And hopefully we can prove that. Now, as I've said before, I think the best way to solve these problems is through cross multiplication. So I'm going to rewrite this equation in its cross multiplied form. The variable that we want in this case is P2. That's the unknown. So we need to get it alone. And the way to get it alone is to divide both sides by T1. They're stuck together by multiplication, so we would have to divide. T1 will cancel out, and we're left with the equation P1 times T2 over T1. You might remember what I said before about the pressure, though. We're going to use atmospheres in this class. So before I can plug in, actually, I need to go back and convert my pressure units. Okay, so I drew a little conversion chart down here, and my given, which goes in the top right, is 745 millimeters of mercury. It's not going to fit. Now, you should know that whatever units are up here on the top left need to go in the bottom right, so I'll pop them in the bottom right. And the units I want to convert to are atmospheres. So what we need to remember is the conversion factor between millimeters of mercury and atmospheres. Seriously, take a sec and go find it. And if you didn't go find it, that's frustrating. 1 atmosphere is equal to 760 millimeters of mercury. That's an equivalency statement, and we can write 2 conversion factors from that, which I hope you did, and you would come to the conclusion that 1 atmosphere is equal to 760 millimeters of mercury. Now that vertical bar just means multiply, so it really shouldn't give you any kind of extra stress. And what we're doing is 745 times 1 divided by 760. That's about 1. I'll calculate it. We get 0.98 ATM. Now that was my P1. So what we had to do was convert the pressure units so that they were in atmospheres, because we'll always use atmospheres in this class. It'll become really important when we get to the next equation, the ideal gas law. And with that, now we can plug into the equation that we have here. The P1 we just found is 0.98 ATM. The final temperature was 273 Kelvin, right? Yes, 273 Kelvin. And T1 is 295 Kelvin. So the temperature is cooling off. Between T1 and T2, it's going down. And so my pressure also should go down. Let's calculate it. When I put it in the calculator, I get 0.91. 0.91 what? Well, Kelvin, just like before, on the top and bottom, cancels out, leaving behind just units of ATM. Now, if you wanted to, you could have kept it in millimeters of mercury and then converted to ATM at the end. But at the, this is the answer that I'd want us to see. And let me highlight the things that you should have in your guided notes. Again, almost everything. Definitely the conversion for pressure. Definitely the algebraic manipulation of the equation. Certainly the work. And obviously the answer. Yeah, I said I was going to do 4, but this is taking me a long time. So we'll do 1 more together. And then if you feel like you're getting it, we can stop. So yeah, I'm going to skip over example 3 and move on to example 4. Example 4 says we have a gas with 1 mole. So that's an amount right there. 1 mole of a gas has a pressure of 1.5 atm. There's your pressure. And its initial temperature is 20 degrees Celsius. It occupies a volume of 3 liters. Oh, I can't exactly underline that. It's in my way. I want what pressure. So I'm solving for pressure. If the volume is increased now to 4 liters. Oh, that's in the wrong spot. And the temperature has also increased. The temperature is increased to 30 degrees. So obviously, let's write down our variables. So we know the amount is 1 mole and the pressure is 1.5. The temperature is 20 degrees Celsius. And let me just add 273 to that, because if I don't, I'm going to forget. So my initial temperature is 293 Kelvin. The initial volume is 3 liters. Since all of those variables are given, I'll be looking for them in the final. It says what pressure, so I don't know the final pressure. What pressure does the gas have if the volume is now 4 liters? The temperature is now 30 degrees, which again, let's just add 273 to it. So that's 303 Kelvin. It doesn't tell me anything about the moles. And so what that means is that the moles aren't changing. The number of moles are going to be the same. And so I'm just going to cross them off. If it doesn't tell you an update on the amount or any of the variables, if it's like, oh, it's at 20 degrees, and then it doesn't say that the temperature changes, that's implied that they're the same. And so we're just going to cross them right out from my equation. So there's the combined gas law. And again, the number of moles doesn't change. So I'm just going to cross them off. Now, if you want to put in 1 mole for both of them, you absolutely can. And you're going to get the same answer because you're going to end up with 1 and 1 on the top and bottom. They'll just cancel out. I'm going to cross them off at the beginning because I'm dyslexic and I don't like numbers. You can do whatever you want. Cross multiply here. Let's do it. So all I did was use the equal sign as a medium to cross multiply. And I got P1 times V1 times T2 equals P2 times V2 times T1. What variable is unknown? Well, if I read my variables here, I'm missing P2. So I'm solving for this variable right here. How do I get it alone? This was a little bit harder, but I just need to move V2 and T1 over. And since they're all hooked up by multiplication, I'm just going to divide both sides by V2 times T1. Divide both sides by V2 times T1. That means my V2 cancels on this side and my T1 cancels on this side. And I can algebraically isolate for P2. Hopefully this is making sense. It's hard for me to know if it makes sense when you're not there to tell me. And email me if it's not making sense. So I'm just going to plug in. My initial pressure is 1.5 atm. I will always put my units in because I like to cancel out units. It's, one of my things. And I hope you'll put your units in there too. The V1 is 3.0 liters. This is why it's so handy to write down the variables, because if you didn't, then you're trying to read the problem for them. Plus T2. T2 is 303. Whoops. Plus, you're much more likely to forget your conversion, for example, to Kelvin in this case. The T2, all of the temperatures have to be in Kelvin, and I did that off to the side over here when I was writing down my variables. If you don't write down your variables, then you have to remember to convert them as you go, and that's complicated. Okay, V2 was 4.0 liters. And my T1 was 293 Kelvin. Before I actually do any calculating, let's cancel out my units. I have liters on the bottom right here, which cancel out with liters on the top. I've got Kelvin on the bottom. That cancels out with Kelvin on the top. And that's going to leave me my units. The only units left over are atmospheres. So how do we do this? Well, you multiply the top, you multiply the bottom, and then you divide them. So 1.5 times 3 times 303. That's 1363.5. And then on the bottom, you'll do 4 times 293. On the bottom, that's 1172. And then you just divide them. 1363.5 divided by 1172. The units here are ATM. Those are the only units that are left over. Everything else canceled out. This problem was a lot harder than the previous ones because more than one thing is changing. So in this case, the volume changed and the temperature changed. I wanted to find out what happened to pressure. It's not a simple relationship anymore. They're more complicated, but absolutely doable using the combined gas law. So in your guided notes, you'll obviously need to have the variables written down, which I'm highlighting in yellow right now. I want you to have the combined gas law, or at least the cross-multiplied version of it. Make sure you know how to do this. If you're struggling on the combined gas law, please come and see me. Let me know how I can help. And then I want you to plug in. I want you to show your units canceling. You don't have to show that intermediate step as long as you're able to get 1.16 as your answer. This screencast is already longer than I want it to be for anybody. So you know what? I'm just going to have crossed out problem 3. You won't see it. But it's not a bad problem to have and to go over. Maybe we'll do it as a bell ringer, because this problem has, and I hope you haven't signed off yet, this problem has amounts in grams. Grams is not how we measure amount. Do you recall how we measure amount? It's in moles. So what we would need to do with this problem is convert grams to moles. And to do that, we need the molar mass. So you'd say, okay, well, I've got 4 grams of helium. Whatever units are here, whatever units are in my given box, need to go down here. And the units I want to get to are moles of helium. So what we need right here is the molar mass. We literally need the molar mass of helium to do this problem. And you know what? We're just going to have to do it another day because we're out of time. So yeah, thank you for watching. I'm sorry. I want to keep them under 10. I'm doing my best. I hope this was helpful. And if it wasn't, please let me know. I'll see you next time. Thanks for watching. Bye.